Okay, hi everyone. So in this video, I'll be going through the remainder of the slides from your first chapter, which was the preliminary chapter. So these are just the things that you will need to know to get started in the first topic, which is metric spaces. So the things on these slides is just a summary of what is in that chapter one. So when you have a look at that chapter one, which is the preliminaries, there's a lot more information in there. So you have to read through all of that. What's on the slides here are just what we need to get started into the actual course content, which is metric spaces. So in class, the last thing that was talked about was this characterization terms. So the characterization terms is just, you could think of it like another way of showing that something is an infimum or a supremum, because a lot of times in these proofs, for example, the supremum, we know that that is the least upper bound. So if you want to show something is a supremum, showing it by using that definition might be a bit difficult. So we want a way to write this, something being the least upper bound in a way that will be useful for us when we go to do proofs. So this first one is the characterization for the infimum, and it basically says that beta 0 is the infimum of some set S if and only if. So that means these two statements mean the same thing. Sorry, if and only if the following two conditions. So beta 0 is the infimum means the same thing as these two conditions. The first condition, so if you want to show something is the infimum, this is one way you could do it. You have to show it satisfies these two conditions. The first one is that beta 0 is a lower bound for your set. And the second one is that for any epsilon, so for any small number, you could always find some element in your set, let's say x0, that lies in between beta 0, which is what you think is the infimum, and beta 0 plus epsilon. Another way of interpreting this second condition is that if you take any epsilon, no matter how small, and you add it to the infimum, so you get beta 0 plus epsilon, this new number will not be a lower bound for that set. So if you have in this example, let's think of it like numbers. So in this example, if beta 0 plus epsilon is not a lower bound for S, then that means that there's some number from your set S that is less than it. Okay, because if it's not a lower bound, then there must be an element of your set less than it. So that's what this characterization is saying for infimum. For the supremum, we have the same thing. So alpha 0 is the supremum of your set if and only if these two conditions hold. So it's the same sort of condition. Alpha 0 first has to be an upper bound. And for any epsilon, no matter how small you make it, you could always find an element y0 from that set that lies in between alpha 0 and alpha 0 minus epsilon. So said another way is that alpha 0 minus epsilon is not an upper bound for S. So if you have something you think is the supremum, what you have to do is show that if you subtract any small amount, any small number from it, any epsilon from it, there's going to be an element y0 from your set that is now bigger than it. Okay, because if a number is not an upper bound, then that means there's another number in that set that is bigger than it. Because upper bound means that you are greater than everything in that set. So if you are not the upper bound, there's something in that set, so y0, that is bigger. Okay, so if you could show those two conditions, that's the same thing of saying alpha 0 is the supremum. And these infimum and supremums, they have a lot of nice properties that would be useful to know. So let S be a non-empty subset of real numbers that is bounded, let's say both above and below. Okay, so since we are in the real numbers and this set S is bounded above and below, then we know that by the completeness property of the real numbers, it has a supremum and it has an infimum. So the first condition is something that should be kind of obvious, that the infimum of a set is always less than or equal to the supremum of that same set. The second one, B, is saying that if now you consider the set minus S, okay, so remember S is just a subset of real numbers. So we're just thinking about regular numbers for now. So the set minus S, all you do is you just take all the elements in S and you just negate all of them. So that's the set minus S. The supremum of this new set minus S is minus the infimum of the original set. So in some sense, you could just think of it like if I pull the minus sign outside of the supremum changes into an infimum, right? And another way of saying this, so now if you replace here by the infimum of S, if you replace S by minus S, you will get this result. So the infimum of minus S is equal to minus the supremum of S. So it's the same thing. If you think of it like you're pulling the minus sign outside, infimum changes to supremum, and supremum changes to infimum. The another set of properties is if A and B are bounded subsets of real numbers, so again, just regular numbers, and it's bounded, so it has the infimum and supremum. In this case, A is a subset of B. Then we get these relationships. The infimum of B is less than equal to the infimum of A, and the supremum of A is less than equal to the supremum of B. So the first time you see this, well, all of you would have seen this at some point, but um, I'm sure that the first time you saw it, it seemed kind of strange because if A is a subset of B, so A is inside of B, how is it that the infimum of B is smaller than the infimum of A? So you might have thought that, wouldn't it be the other way around? Shouldn't it have been the infimum of A is less than equal to the infimum of B? And it's very easy to see an example of why this would be the way it is. So if you think about the natural numbers and the integers, so A is the natural numbers. They are inside of B, the integers. Okay, of course, that those sets are not bounded. What is a good example? Let me see. Right here. Okay, so just for an example, so A is a subset of B, right? So let's just take for example, let's just say A. So let's just say we have some finite set, right? No need to talk about infinite sets. We could see it by just looking at finite set. So A, let's say A is 1, 2, and 3. Then of course the supremum of A is 3 and the infimum of A is 1. And let's say B is 0, 1, 2, 3, 4. Then the supremum of B is 4, and the infimum of B is 0. So of course, in this case, A is a subset of B. That's what we want. And if we look at the infimum, for example, the infimum of A is 1, and the infimum of B is 0. So we get that the infimum of B, which is 0, is less than equal to the infimum of A, which is 1. And this is what the result is saying. Okay, so it's kind of easy to see why this would happen. It's because, and the same thing happens with the supremum, is because if B is a bigger set, so think of it like this, if B is a bigger set, you are adding more numbers into it. So if you're thinking about the supremum, okay, let's think about the infimum. If you're thinking about the infimum, which is a lower bound, and you take the set A and you add more things into it, well, the smallest number, so you can think of the infimum as like the smallest number. If you add more stuff to it, that number could only decrease. That smallest number could not increase because I'm adding things to it. So if you add stuff to it and you make a bigger set B, the smallest number could only get smaller. So that's why we see that the infimum of B is less than infimum of A. And the same sort of thing you could reason out for the supremum. Okay, let's go back to the slide. Right. Yeah. So the infimum of B is less than equal to the infimum of A if A is subset of B. Right. Okay. And the supremum of A is less than equal to the supremum of B. But if we look at part A, the property A, it says that the infimum of a set is less than or equal to the supremum of that same set. So if you look at A for the second property, we could link this together because we know that the infimum of B is less than or equal to the infimum of A. And we know from part A above that the infimum of A is less than or equal to the supremum of A. And the supremum of A is less than or equal to the supremum of B. So we could write all of this like what they have here for B. We could link all of it in this chain. Okay, and you got a relation with all of that. All right, so that brings us to maximum and minimum. So if you, so a finite set of numbers, which was the example that I gave, always has a supremum and infimum that is contained in the set itself. Okay, so if that seems kind of weird, then you need to sit and think about why that is true. Right, so if a finite set of numbers has a supremum and infimum, then those things must be in that set. When the supremum and the infimum belong to the set, we sometimes don't use these words anymore, supremum and infimum. We want to emphasize that these elements are in the set. So how do we emphasize that? We use the word maximum and minimum. So the maximum of a set is just the supremum of that set if it happened to be in that set. So if the supremum of a set A happens to also be an element of A, we know this does not always happen, then we could say instead of supremum A, we could write max A or maximum of A. It's the same number, by the way. It's the same number. So the max A is equal to the supremum of A. And same thing for infimum. If the infimum of a set A happens to belong to that set A, then we could replace the word infimum by minimum. Okay. So here's an example. So again, we have a finite set, but it doesn't have to be a finite set. So in this set, 1, 5, pi is about 3.1, E is about 2.7, and then you have 7. So the max, or let's look at the supremum. The supremum is 7, and 7 happens to also belong to the set, so that's the maximum. The minimum, the smallest number in this set is 1, so that's the So 1 is actually the infimum. So 1 also belongs to the set, so it is the minimum of that set. Yeah, so now we're going to talk about two very useful properties that is used in pretty much almost every proof in analysis. In some shape or form, they always make use of these properties. One is called the Archimedean property of the natural numbers, and the other one is called the dense property of the rationals or the irrationals in R. Both of them will look. So let's look at the Archimedean property first. So the Archimedean property, you could think of it, so there's actually many different ways of saying this property, and they're all equivalent. So they will all work. But here's one way. If you have two real numbers, x and y, and let's just say x is positive, right? So let's just say one of them is positive, then there exists, so you could always find some positive integer n. So this is a natural number. You could always find a natural number such that n times x is bigger than y. So if you think about what this thing is trying to say, it's saying if if uh if you have a number y, right? So y is your number, and my number is x. And let's just say again, x is positive. No matter how large your number y is, I could always find a natural number n such that when I multiply n by my number, my new number is bigger than yours. Okay, so you can think of it like you could always boost x arbitrarily large to be bigger than any real number, any y. And here are three other ways of saying it. Okay, so the following statements are equivalent. So the Archimedean property holds, that's this theorem. Another way of saying that is that if for each real number z, there is a natural number n such that n is bigger than z. So for any real number you could think of, z, I could find a natural number bigger than it, right? So that's nothing too new for you. So another way of saying the second point is this third point, which is the set of natural numbers n has no upper bound in R. Or in other words, the set of natural numbers is unbounded above. It's bounded below, by the way, right? It's bounded below by, well, any number less than 1 will bound n below, but it has no upper bound. So you could get arbitrarily large. And this fourth property is used a lot for any real number, x, if x is positive, you could always choose a natural number n large enough so that 1 over n is small enough to squeeze in between 0 and x. Okay, so for any positive number you have, so think of any positive real number. Let's say that real number is very, very small, very close to 0. So x is bigger than 0. So let's say x is very close to 0. No matter how close that number is to 0, I could always find a natural number that's very large so that when I do 1 over it, so 1 over a large number is a small number. So when I do 1 over it, I get a number that's smaller than this x. Okay, so in other words, if you can make any natural number arbitrarily large, you can make 1 over that and not 1 over a natural number arbitrarily small. Yeah. So Archimedean property. Right? You should try to prove them. So the following statements are equivalent means each one implies the other. So you can try to prove, assume one is true and try to prove another one. Right? So the second one that we need is this thing called the dense property, or the density of Q in R. This one just says that if x and y are real numbers, and let's just say x is the smaller of those two, then you could always find or there exists some rational number p such that p is in between x and y, right? So we say, in other words, q is dense in R. We'll meet this word dense later on when you all have to study nowhere dense sets and those things. So said in plain old English, this just means that between any two real numbers, any two numbers you choose, you could always find a rational number in between there, right? And that should be no surprise to you. So from this theorem, you could show the same thing is true, not only for the rationals, but for the irrationals. The same thing is true. Between any two real number, you could find an irrational number, let's say q, such that q is in between. So if you pick any two real numbers, of course, those real numbers that you choose, those x and y, could be, well, they have to be either rational or irrational, right? But it doesn't matter what these x and y you come up with. Between those two numbers, you will always find a rational number and an irrational number. Okay. And how to prove that you could find an irrational number if you know this theorem 1.5.8. So you have the proof here is 1,9. You just replace x in this theorem by x over root 2 and y by y over root 2, and you multiply through by root 2. Okay, so you could try that. So this one is used a lot as well. And the reason why this one is useful is because the rational numbers are countable. So between any two real numbers, we might want to make like a countable set of points and then make like a sequence or something. We'll see later on. Yeah, sure. You get this property. So if you want to look at the proof of this thing, you could see it in book, and it has the proof of it. In fact, this is like how the real numbers were constructed. So the real numbers is of course q with q complement, the irrational numbers. So how did they get those q complements? So they fill in the gaps in between q. So now if you take any number, that number is either rational or irrational. You should be able to find another rational or irrational arbitrarily close to it, because that is the way the real numbers are constructed. Okay, so you can look at the proof of it if you want. Okay, so the extended real number system and convention. So okay, I'll explain why we need this later on. So in addition to the real numbers, there is another number system called the extended real number, and we use R with a little star. It's pretty much the real numbers with two new symbols, right? One symbol is minus infinity, and the other symbol is plus infinity. Okay, and we define x, so any real number lies in between these two symbols. So remember, this less than sign is an order relation. So if we add two new elements, this symbol for minus infinity and another symbol for plus infinity, we need to say how does it fit in with the order relation for all the other elements. And this is it, how it fits in. And it also satisfies, so that's how it works for the order relation, right? But it also has to sort of be compatible with the arithmetic in the real numbers, because the real number is a field, right? So how does it play with the arithmetic? Okay, so if x is any real number, then if you do x plus this new symbol infinity, you get infinity. If you do x minus infinity, you get minus infinity. If you do x over plus infinity or x over minus infinity, you get 0. And now you're seeing these things, and these are things they told you in your first year calculus course not to write. Okay, that's because it's not that it's wrong, it's just that we'll see in a bit why it's sort of useful to have these symbols. The second point is if x is positive, then if you take that positive number and you multiply it by plus infinity, you get plus infinity. If you multiply by minus infinity, you get minus infinity. And if x is negative and you do the multiplication, the sign on that infinity flips. So the plus becomes minus, minus becomes plus. Okay. And so now you're thinking, well, why are we doing this? Because it seems like we were told never to do this sort of thing. So the main reason why we're doing this is because um, when you have to calculate like integrals and stuff later on, and it happens that, let me say, integrate some function and it's blowing up. So let's say you want to write that the integral is equal to like infinity or something. Or in this case, it will be like the supremum and the infimum. So you want to be able to write that the supremum of a set is always equal to something. Okay, so if you think of the natural numbers, and I asked you for the infimum, right? Then the infimum of the natural numbers, well, that's just zero. We could write that. Oh, sorry, one. We could write that, no problem. But what is the supremum of the natural numbers? Well, it's not bounded above, so it doesn't have a supremum. Okay, but you still want to be able to write the supremum of it equal to something. Then you just, so that's where you use these symbols to sort of say, okay, it will be equal to this thing. So if a subset S of real numbers is not bounded above, right? So like in actual numbers, instead of, or another way of saying that the supremum does not exist, we could simply say, or we define that the supremum of that set is equal to plus infinity. And if it is not bounded below, instead of saying, okay, then the infimum does not exist, we can now say that the infimum is minus infinity. So now we can write these things to mean like it doesn't exist, but in what sense does it not exist? Um, yeah, and you will also need this stuff for the empty set because the empty set has this weird property. So the supremum of the empty set happens to be minus infinity, the supremum, right? And the infimum, which is supposed to be small, happens to be plus infinity. Okay, so that's why in everything that came before, so if I go back and stuff, you see that we always add, let me see if I correct. Yeah, so for example, 1.5.4, if I go back, in the statement of these things, we always say, for example, let S be a non-empty subset, non-empty, right? If we remove that non-empty thing, then if you look at the first result here, that the infimum of a set is less than equal to the supremum of a set. That's not true for the empty set. So that's why you always have to remember in your head, okay, I always need to remove this sort of annoying case for the empty set. So I always need to add on my statements, non-empty subset, right? And you can look up these proofs. Will it prove for the supremum of the empty set and the infimum of the empty set? Like many proofs involving empty set is like one of those vacuous proofs. Okay, so just something to be aware of if you have to deal with the empty set. Okay, so this has been a typo here. So I have to make sure I fix this. Um, it should be not infimum of S, but infimum of the empty set, right? So the supremum of the empty set is minus infinity. The infimum, this should be empty set, not S, empty set. Infimum of empty set is plus infinity. Okay, and now we have the complex view. So you're all already familiar with what the complex numbers is, but let's just recap it. So a complex number, you could think of it as an ordered pair, AB of real numbers. So the set, just the set with the complex numbers without any arithmetic on it, is then, so we use this fancy C, the set of all ordered real numbers A comma B. And now you're looking at this set and you're saying, but isn't that set the same as the Cartesian product of R with itself, R cross R? And the answer is yes, it is the same set. So R cross, so this is why and even as far back as high school, when they were teaching you the complex numbers, they would draw the argon diagram, if you remember that, and they would use R squared, the plane, to denote complex numbers. So what is R squared? That's just R cross R. So the complex plane, which is C, is the same thing as R squared or R cross R. Okay, well, of course, that's just a set. Okay, so that's the set. If you want to convert the complex number now into a field, we need to add the addition and the multiplication, okay, to give that field structure. So how to add two complex numbers, how to multiply two complex numbers, how to tell whether or not two complex numbers are equal. So that's given by this definition. So if x is the complex number a comma b, and y is the complex number c comma d, these two complex numbers are equal. So that's this first point, x equal y, if and only if a, so the first component is equal to, well, the first components in each complex number are the same. And also the second component in each complex number is the same. So if and only if A equals C and B equal D, then you could say your complex numbers are equal. Okay, how to add two complex number? You add them component-wise. So A adds to C, and that gives you first component. And then B adds to D, and that gives you second component. And now you're thinking, okay, but isn't this just like addition in R squared? Yeah, it's the same addition in R squared. Okay, so far, nothing in the first and second point is different from the arithmetic that you have on R squared. What makes the complex numbers different now from R squared is this rule, the multiplication rule. Okay, so now the multiplication rule, x by y, how to multiply two complex numbers together. So you see, it's something that looks kind of weird, but it's a by c minus b by d, and that's the first component. And the second component is a by d plus b by c, right? So this is what makes the complex numbers different from R squared. It's this multiplication, right? And we'll see where this I comes in, the imaginary number I. So for this theorem, so the first one, if you want to, because I know some of you are taking algebra, you could sit down and convince yourself that C, the set that we defined before, or the set of all ordered pairs of real numbers, with that addition and multiplication satisfy all the field axioms. So it's a field. Now what we want to observe is that for any real number, A and B, if we have 0 in the second component, so the complex number, you could think of it as our ordered pair. So A comma B or X comma Y, right? What happens if the second component for the complex numbers, what happens if I set all of that to be 0? And I follow the addition and the multiplication given before. Okay, so if we follow the multiplication and the addition given before, but I set all the second components to be 0, then I get A plus B and 0. And the multiplication gives me AB and 0. Now, if you now cover up all these zeros, if you go here and you just cover up or scratch out all these zeros, what would you get? You will get A plus B equal A plus B, and you will get A by B equal AB. That's the addition and multiplication for the real numbers. So it appears that we have the structure of the real numbers inside the complex numbers. And so So that's how we would like to say that, you know, uh, so in undergrad and stuff, they would say that the complex numbers contain the real numbers. So technically, that isn't true. Yeah, so technically, that isn't true because how could the real numbers be a subset? Because if you see the real numbers contain the complex numbers, let me see if I can write. Yeah. So if you remember back in high school or maybe even in some way undergrad class, they would see, okay, so we start with natural numbers inside of integers, inside of rational, inside of real, and then they would say the real numbers is inside of complex numbers. So technically speaking, this isn't true because the elements of C, we just define it to be ordered pairs, x comma y. The elements of R is just x. How could you have x elements that look like this being a subset of ordered pairs? So technically speaking, you can't really say it's a subset, but of course, you do have the real number structure inside the complex number. You just need to identify the real number x to the complex number x comma 0, right? So the fancy word mathematicians use is identify. So you identify to a real number a, you identify it with a comma 0. And to a real number b, you identify it to the complex number b comma 0. And that will recreate the real numbers or like an image of the real numbers inside the complex numbers. Okay, so just something to be aware of. So where does this I stuff come in with the complex number? We all know what makes the complex numbers different is that it has like a special element called I, which is the square root of -1. Where does that fit in all these ordered pair? So that whole square root of -1, we could recover all of that from the ordered pair. So the element 0, 1, so 0, 1 is a complex number. We're going to call that element I, right? So we're going to assign this ordered pair the label I. And if you do I times I following this multiplication rule, so now we see why why this multiplication was chosen in this sort of funny way. It was chosen in this way such that when the second component are 0, it recovers the multiplication from the real numbers. And when the first component is 0, and you set the second component to 1, so 0, 1, it gives you an element such that when you square it, you get -1. Okay, so you can actually work this out. So take 0, 1, multiply by 0, 1, and follow this rule. Follow this rule, and you will get -1, comma 0. Right? So we identify -1, comma 0 with -1. And that's the famous I squared equal -1 hidden in there. So that's actually what I is. And so now that we have this I as 0, 1, so we usually don't do arithmetics with the complex numbers in terms of these ordered pairs. We sort of want to reserve that for like elements in Rn. So instead we write it as A plus IB, right? So we use a different notation. It's the same thing. It's the same complex number, and you could do the same calculation. It's just a different way of writing the same thing. So instead of writing A comma B in terms of these curved brackets, because we want to reserve this for studying elements in Euclidean space. So instead of writing A comma B, we write it as A plus IB, right? And of course, we have something called the complex conjugate. So if you have a complex number, A plus IB, the complex conjugate is you just change the sign in the middle. So A is the real part, right? So A is called the real part of the complex number, and B is called the imaginary part of the complex number. So the conjugate is you just flip the sign of the imaginary part. And of course, you all have seen these rules at some point, I'm sure, for dealing with complex numbers. So we're going to use these rules later on. So if you take the conjugate of the sum, that's the same as the sum of the conjugates. If you take the conjugate of the product, that's the same thing as the product of the conjugates. So when you're doing addition or multiplication, you could sort of pull apart the conjugate. If you do a complex number plus its conjugate, then that gives you 2 times whatever the real part is. And if you do z minus z bar, you get 2 times the imaginary part. And if you do z bar, then this is a real and positive number except when z is equal to 0. Right? So we'll see this one show up again. Anything else? Yep. So just like we could take the modulus or the absolute value of a real number, you could do it for a complex number. It's actually the same formula. So the absolute value of a complex number. So if you now think back to what is a complex number in terms of the xy or the ab coordinates, right? Then the length of that's just Pythagoras' theorem. So I write it. Okay. So if we think again of a complex number z as being this a comma b, right? Then the length of z is just the square root, is Pythagoras' theorem of a squared plus b squared. And it turns out that this formula here, you could show it's the same thing as if I do z bar, I want to say to the power of a half, right? So you could verify this. So the modulus of a complex number is the same thing as z bar to the power of a half, or the square root of a squared plus b squared. Right? Yeah, so square root of z bar. Note that if x is real, then of course x is equal to its complex conjugate because there's no imaginary part. And the modulus is the same thing as if you square root the square of a real number. And of course, the modulus function is defined like this. So in terms of the modulus of complex numbers, how does that behave with products and addition? So if z and w are complex number, then the magnitude, so think of the modulus as the magnitude of the complex number. So the magnitude of the complex number, so modulus of z, is the same thing as the magnitude of the conjugate. So when you take the conjugate in some sense, you don't change the magnitude of the complex number, you just change the, well, if you think of it like a vector, you change the direction that it's pointing. And the modulus of z times w is the same thing as the modulus of z by the modulus of w. The modulus of the real part of the complex number is less than or equal to the modulus of the complex number. So what this part C, and we'll see it in a few proofs in the next chapter, what this part C is saying is that the magnitude of the real part of the complex number is always less than or equal to the magnitude of the entire complex number, right? So the real part is always smaller than the entire complex number. And you might be thinking, okay, could you replace the real part by the imaginary part and still have this inequality? The answer is yes. Okay. And part D, very important, it's triangle inequality. So the modulus of z plus w is less than or equal to modulus of z plus modulus of w. Right, so you could see root and textbook for this. Or if you want, you all could probably prove this, right? If you take Z as equal to A plus B times I, and W may be X plus Y times I, and just do the calculation and verify that the left-hand side is equal to the right-hand side. So Schwartz inequality. So the proof is in your course notes. So this is going to come in handy when we have to talk about LP space. So all it's pretty much saying is if you have n complex numbers, A's and n complex number B's, if you take the sum of the product, notice that the B's have conjugate over them. And you take, so if you take the summation inside, so the summation part, all this is going to give you is a complex number. Okay, so the sigma A, J, B subscript J conjugate, all that summation is giving you is just a complex number. And if you now take the modulus of it, right? So the modulus will give you a real number and you square that real number. Okay. So this is telling you what happens if you were to push the modulus inside. Okay, so you move the modulus inside of the summation. You don't get an equal, right? You don't get an equal. It's less than or equal, right? You lose something. So if you push the modulus inside and you split up what you have inside, that's less than or equal to the summation of modulus of the A's squared multiplied by the summation of the modulus of the B's squared. Okay, and the proof is inequality. Okay, so this is a famous inequality. And you could think about what will happen. So we'll see this later on. What will happen, because we know real numbers could be identified as a special type of complex numbers. So what happens to this inequality? It will still work if A's and B's are real numbers. Okay, because this inequality is for complex numbers. But real numbers are could be identified as complex numbers. So the inequality should work for real numbers as well. And in the real number case, of course, the B's, when you take the conjugate, if the B's are now real numbers, then the conjugate just goes away. It doesn't matter. Okay, so that's the form. We'll see it then later on. Yeah, so if Z1 and Z2 are two complex numbers, so okay, we already went through triangle inequality. And the second one is again very useful. You see it in a lot of proofs. It's something called reverse triangle inequality. Yeah, so you have triangle inequality and reverse triangle inequality. Yeah, so this just tells so we have where we're heading. So we're going to start learning about metric spaces and these things called norm linear space or norm vector space. So of course, you know what is R to the power of K. That's just R Cartesian product with itself, K times. And that's just a string of K real numbers, and we call those points. Okay, so you guys can read that. Yeah, so how to add elements of Rn and how to multiply, how to do scalar multiplication. So we know that. We know that Rn is a vector space over R. So now we need to remember your axiom of a vector space. So Rn with these operations form a vector space. And on a vector space, we could get something called an inner product. And there's a special type of inner product called the dot product for Rn. Of course, you all learned this in high school. This is the dot product in Rn. The norm or the Euclidean norm, you all will end up learning about a bunch of different types of norm. But the Euclidean norm is just the dot product of a vector with itself, and then you raised to the power of a half. Yes, so I should probably remove this dot here. That dot kind of confusing because is it the because we're already using dot for dot product and bracket for inner product. So this dot here, I will change it anyways. This dot here should be a comma. So it should be our bracket x comma x to the power of a half. Okay, but you have the formula for it here. So that's how to take the length of a vector in Rn and Rn. I know I keep saying Rn and you're saying Rk, but I'm just used to Rn. Together with that inner product, that dot product is called Euclidean k-space or k-dimensional Euclidean space. And we have a bunch of properties for this norm. Okay, so remember these properties, we'll see them in the next chapter when, well, we'll recap all these properties again in the next chapter because we'll see that some of these properties are very closely related to that for a metric. Okay, because the norm is closely related to how a metric works. So I put here properties 1, 2, 3, and 4. Oh, sorry, 1, 2, 3, and 5 are precisely the definition for a general norm on an arbitrary vector space. Okay, so before, this was the Euclidean norm. That is just, which is another name for the dot product. So the dot product is a special type of norm. It is a special type of norm for Rn, and this is how it is computed. Okay, but there are many other norms for Rn, and we will learn many other norms for many different types of spaces. So what is a norm? A norm is just a function that satisfies 1, 2, 3, and 5. Those properties. So any function that satisfies those properties is a norm. Okay, so we'll see that in the next chapter. I don't need to go into too much detail with that one. Okay, so hopefully that